Biometrics such as Face ID, irises, fingerprints, voice recognitions are used for identification and authentication, and usually the databases, the biometric databases are deployed without cryptographic protection, and if a biometric database gets compromised, that would last a lifetime, meaning that so if a database containing your password gets compromised, you can easily change that, but it is not going to be the same for your biometric data. You cannot change your fingerprint or irises as easy as you can change your passwords. One of the main property of biometric readings is that they are noisy. So the further reading of one biometric might be different from the initial one because of some environmental situation. So as we see here, the further reading of an iris might be different because a part of the eyelid has covered the iris, or the position of the iris is different, or the accuracy of the camera or light of the environment. If the further reading are within distance t of the initial reading, we call those readings close, and we regard them as being they belong to the same people. While if the further reading are within distance c times t, where c should be some value greater than 1, we call them far readings, and as you see, they belong to different people because they should be completely different irises or biometrics. The goal of the proximity search is that if further readings of a biometrics, which we call them query, are close enough to a database record, those records should be returned. And when we are talking about close and far, our metric to determine that is Hamming metric, and how Hamming metrics work, how Hamming distance work is that consider we have two value to strings x and y. Their Hamming distance is the number of positions that they are different. So in this example, x and y are different in the second position from left. So, and that's the only place, so their Hamming distance is 1. And as I said before, closest strings are those which their Hamming distance is at most t, and far strings are those strings that their Hamming distance is greater than c times t, where c is some value greater than 1.
I think whenever somebody joins what takes control over.
Yeah. So as I said, the goal of the proximity search is to return all the database records that their Hamming distance from the query is at most t. And what we are looking forward is that this result set size be 1. So whenever we have a query, only a biometric of just one person is returned. In that case, we call the system accurate, and this is important because we don't want anyone to identify themselves as the other people. So in an accurate system, if one person query their iris through to biometric database, only one, which is the closest biometric, is returned. While in an accurate system, upon receiving a query, more than one biometric of the people is going to be returned, which may or may not include the actual one. Now let's go through some definitions that are important to understand the rest of the talk. We are going to talk about the well-spread databases, approximate proximity search, locality sensitive actions, and multi-maps. We call a database well-spread if two conditions hold. First is that all records in the database are far from each other. And second, if an external query is close to at most one of the records in the, if we have an external query, it should be close to at most one record in the DB, not more than that.
How are those different?
So if we shouldn't have the case that the query is in between of two different records in the database. So in that case, we would return 2 because it's exactly in the middle.
If C is at least 2, then 1 implies the second condition. Otherwise, it doesn't. What does close mean? Sorry.
So close is to have the distance of at most T from the records.
And far
Is
C.
yes. Okay. So approximate proximity search scheme, like many other searchable encryption schemes, contain 2 main functions, setup and search. Through the setup, the data owner would encrypt their biometric data set and encrypt it using their own key and send it to a remote server. Through the search, a user would query their intended biometric using some token that they got and query the value y to the remote server. And then server would turn back the result value j, which if the system is correct, the values inside j must be close to the queried value y. In other words, APSS is an approximate proximity search scheme if for all well-spread databases and all query y's, it should be true that the far records from the query are returned with probability of 1 minus some predefined negligible value delta far, and the probability that close records to the query are returned should be greater than 1 minus some negligible value delta close. The next primitive that we are going to use is locality sensitive hashes. So LSHs are a family of hash functions that they map close items to the same value more frequently than they map far items to the same value. So if x and y are close, then probability of evaluation of LSH h over x be equal to h over y is greater than some epsilon t. And if x and y are far, then the probability of having h of x be equal to h of y should be less than some value epsilon f, with the condition that epsilon t is always strictly greater than epsilon f. So as an example, let's see we have LSH1 through to LSH5, and we have 3 biometric readings y, x2, and x3. In this case, y and x2 are obviously close to each other, and x3 is very different from the rest. So x2 and y have 4 common LSH evaluation out of the 5, but x3 is has completely different LSH evaluation from y and has 4 different LSH evaluation with x2 out of 5, which is white, black, black, white, white, black, black, and white, black. The next thing that we are going to use is a data structures called multimaps. Multimaps contain 2 operations. One of them is add, which add the key value pair to the data structure, and the other one is retrieve, which upon receiving a key, the data structure would return all the values that are associated to the key. And as we see, we can associate many values to one key, so it's a one-to-many relation. Now having all these primitives, let's see how the baseline scheme works. Yeah. Okay, so for the baseline scheme, the same as before, we have setup and search. Now we are going to use the definition of multi-maps and LSHs to construct the baseline scheme. So we would compute the evaluation of all the LSHs over all the records and associate each LSH evaluation to the index of each record. So here for X1, we have LSH1 evaluation of X1, LSH2 evaluation of X1, through to LSH n evaluation of X1 as being assigned to index 1. The same is for X2 and up to Xm. Later, through search, we are going to return any record in the database that share at least one LSH evaluation to the query. So it's a disjunctive search. We are going to see if if there is a record that has common evaluation on LSH1 or LSH2 through to LSHN. The drawbacks of baseline scheme is that the construction of zero leakage multi-maps is proved to be impossible, and we are going to have at least the search equality or query equality pattern getting leaked. The other thing is that to reach the accuracy that we talked about in the previous slides, the number of required LSHs, which is n here, should be very large. And when we are talking about large, we mean in the order of millions. Yeah.
Something within, why can't I do something really dumb? The good news is that I have nice strict equality for the things that I'm trying to get from the data.
Yeah.
So does private information retrieval just solve this problem? I mean, can I just privately query the database with each of my LSH values and then get ask the database, you know, there, I get a match then. Sorry. So yeah, so does PIR just solve this problem?
So I think for
this isn't a trick question, by the way.
Yeah. So it depends. I think the PRI only in a traditional way only protect the query privacy. I don't know if the response is going to be private.
Yeah, you can encrypt. The issue here is the map. So what you just said is fine if there's one thing associated with each keyword, right? But now I need some way of knowing, well, I need to know the count of how many things I'm supposed to retrieve, and I need to look up that many things. So if the maximum number of things I have to look up is a constant, well, you're fine. But if it's not a constant, and you need to, like, there's a whole line of works on like how you pad buckets in the right way so your storage isn't too much.
I see. Okay, so if we didn't mind the complexity ramifications of this, PIR would be fine. I just carry out a PIR for each one of the LSHs.
And you make each thing the maximum result set size.
Sure.
Then that's fine.
Then that's fine.
Yeah, the impossibility result is if you want your total storage to be the maximum number of values rather than the product of the number of values times the maximum like number of things that can be associated.
Okay, I didn't get everything, but I think I understand.
Yeah.
I think I understand basically.
Yeah.
Okay.
But other than the privacy issue, the main thing we care about is to lower the number of required LSHs. And that's why we want to move from using a multi-map. Having seen the drawbacks of the baseline schemes, we are going to see how we are going to use maps, and error correcting codes to reach the accurate search. So as we said before, the goal is to return the records to be more likely to be relevant to the query. And for that reason, we are also going to need to lower the probability of repeating an LSH evaluation across queries. So we want different LSH evaluation for each record. And we want to decrease the number of associated value to each record, to each keyword. And if we are going to move to maps, this decrease means that we are going to move from a one-to-many relationship to one-to-one. So our solution here is that instead of using that disjunctive query, which was having just one common LSH evaluation, to be K out of N common LSH evaluation. And to that end, we are going to use the notation of map to have that only one value being associated to each keyword. And when we are talking about maps have the same functionality as the multi-map we talked about before, insert and retrieve, just that maps are one-to-one. So our approach,
So to finish up Alex's question, it's very easy to. It's straightforward. You just need something to transform keywords into location.
So our approach here is that instead of using XIs, use the shares of XIs and put the evaluation on the multi-map. So we are going to use the error correcting codes, the coding properties of secret sharing scheme, and if we have an iris reading xi, we take the index I, we encode it to have the code word ci, and then we split the symbols of that code word into n symbols if we have an nk code. Then instead of associating each LSH evaluation to the index, we are going to associate the LSH evaluation to the shares of the index code word. So LSH1 of xi would be associated to first symbol of the CI, LSH2 would be associated to second symbol of the CI, and so on through to LSHN. And we are going to do this for all the M records in the data set. Later, through the search process, we are going to see how many LSH we are going to compute the LSH evaluation of the query and see how many of them are common with the keywords in the data set. And we are going to return the common ones. If we have at least K common LSH evaluation, then we are going to be able to recover the code word CI, and consequently, we are going to be able to recover the index of that record. So, and when I'm talking about error correcting codes, assume that we have an encoding and a decoding function. The encoding function receives message M and output the code word C of M. And the decoding function received that code word C, and assuming it has, through the transmission, it might have up to T errors and output the message M. C is called error correcting codes if for all messages M and the T errors, the decoding function is, if the decoding function is able to recover M. For the secret sharing scheme that we talked about before, we are going to use Reed-Solomon codes. Reed-Solomon codes are an encoding function, are error correcting codes that work as follows. Let's assume we have a message M, which has M characters. We are going to put each of the message M's symbols as a coefficient of a polynomial f. And then we are going to evaluate that polynomial f over some predefined distinct element alpha 1 through to alpha n. And these evaluated points are going to form our code word, which is an nk n minus k plus 1 code, and the last one is the distance of the code. To see this as an example, let's say we have a field of size 3 and we want to transmit the message to 1. So we put to 1 as a coefficient of a polynomial, which makes the polynomial to be 2 plus x, or 1 times x. And then we are going to evaluate this f of x over 3.01 and 2. And we are going to get the code word 201. Whenever we have k plus 1 points, we are going to be able to decode a code word that have been constructed from a polynomial of degree k. So as we can reconstruct a line from 2 points. So let's see how our construction works. But before, let's recall the baseline scheme. In the baseline scheme, we were associating the LSH evaluation over the records and associate them to the index of the records. But now we are going to associate the LSH evaluation to the symbols of the code words that's constructed from the index of the records. So here for record XI, we have LSH1 evaluation true to LSHN evaluation of the code word CI. And for the first LSH, we are going to use the second symbol of the code word. For LSH2, we are going to third, and so on. And I'm going to say why we are starting from 2 in a short time. One thing that, so let's first see how the setup works. As I said, we are going to compute the LSH evaluation. Then we are going to initialize a Reed-Solomon code. And we are going to put the first code word symbol to be the index I. That's why when we are going to do the error correction, we are going to be able to recover the index of the record. And then for each of the LSHJs, we are going to put the tuple LSHJ of XI and the code word CI of J to the map. Sorry. Okay. So one of our goals was that to lower the probability of having the same LSH evaluation across the records. To make sure that our construction does this, we run the setup for 100 times and evaluated the maximum number of LSH matches. And we saw that the common LSH evaluation across records was some number between 13 to 18, and in the most frequent time, the maximum number of common LSH evaluation was 14, which was 33% of the times.
So, sorry.
Yeah.
So fixing one record and asking how many different LSHs does it collide with some other record? Or something?
No, I'm not fixing a record. So through the setup, I'm seeing what is the common LSH evaluation across all the records. And I count that. And I do it 100 times. So I run the setup 100 times.
So you're saying there are, let's just take the 14.
Yeah.
There are 14 total times LSH matches
14 is the maximum.
across what?
Yeah, across all the records.
Okay, so
Yeah.
you count across all the records and you ask how many LSHs does some other record have?
And there are different numbers, and the 14 was maxed in just one setup run. And we did it 100 times.
One data structure.
Yeah.
14 is the length of the chain in the map, and you had 30 chains that had this.
Oh, no. So 14 is the number of rows that have the same first element, first common element. So out of the record, saw that 14 of them have the same LSH evaluation.
So
And the 30 is what?
So we run the setup 100 times, and 33 times of that, 14 was the maximum number. And so
the number of setup. This is just, you're going to generate LSHs, that whole matrix. What you're doing is for each row of the matrix, you're counting how many LSHs appear somewhere else in, or somewhere else in the same column.
Yeah.
So how many, so I want to know for each record, how many LSHs does it share with some other record?
the thing is, when
Collision.
But it's just that the key here has.
the key has the J associated to it.
So that's why you only
Always.
give it a column. So you count for each row, what's the maximum collisions in each column?
It can never be the same that LSH1 of x1 be equal to LSH2 of x2 because their first component starts with J.
So
This
maybe,
is the max across all column. Because you're saying like we fix for one column.
Yeah, but we didn't fix for one column. We looked all the columns and we took the maximum value. Yeah.
It's the max of all column.
it's fix one row. How many columns have collision? Now compute the max over all rows. So I want to know across all records stored in the database, what is the maximum number of LSHs that have collision? Okay. Well, okay. Let me ask a different question then. Why do I care about collisions now?
Should I answer?
Yeah. Why do I care about collisions?
Okay, so one of them is that we are moving from multi-maps to maps, and the other thing is that we don't want one query to be identified as the other, so we don't want the code word. If we have enough collisions, then we can decode one code word to be the coding of another irrelevant record in the data set.
But just taking that first point you said.
Yeah.
The second I have a single LSH collision, what you just showed me, I can't instantiate with a map. Because there are things on the left that are equal and things on the right that aren't equal. Yes?
The things?
So if I have a single LSH collision,
Yeah.
then now I have some keyword that has two values associated with it. So I can't build this with a map.
That's right.
So LSH collisions are bad.
Yeah.
Okay. I just,
Okay.
thought, at least Walter and Amir, or Walter and Alex, sorry, I was looking right out, Alex. Is that? Yeah. Okay.
The other thing to avoid multi-map is that if we have the same first components in the map, but the second one be different. So we put a restriction that whenever the first component of a tuple are the same, so we have the same LSH evaluation for some xi and xj, then we force that the K symbol of the code word CI and CJ be different.
Be the same.
Be the same, sorry, yeah.
So pause on that for a second.
Yeah,
So you're going to avoid a multi-map by just, whenever there's a collision, you're making the code word symbols be the same.
yeah,
So this is a constraint on the code.
yeah, we put that in the setup. So whenever we have this condition satisfied, we put CIK be equal to CJK.
Be obvious to me that there even exists an error correcting code that
So,
will also have all of these additional properties.
because we are sampling the codes, we may get different code word symbols. So in the first place, we are sampling the codes and then we are changing some of the symbols to satisfy the constraint we want.
Oh, I see. So first we select the code.
Yes.
Well, we go through and we doctor it up.
Yeah, exactly.
Make these changes.
Yeah, what happens is that first we initialize the RS code and we construct this table, and then we are going to check that condition.
So you basically construct the multi-map, then you reduce.
Yeah, it can be multi-map at some point at the first place. Okay, so after the setup is completed,
Sorry.
yeah.
How do I set them to do the same?
We just changed one of the code word symbol to be the same as the other. Yeah. Well, because we are starting from from 0, then the one that has the bigger index is going to be changed.
You're not going to use that in your now. Any convention for setting them.
Yeah. Okay. Then when we receive a query Y, we are going to compute all the n LSHs over the query Y, and whenever that LSH evaluation exists in our map, we are going to retrieve the associated value as CI J+1 symbol. And if we get enough code symbol, we are going to able to decode CI and retrieve the index I of the.
Sorry, no, I'm confused.
Yeah.
So, but we just took the code and we punched a whole bunch of holes in it. So why can we still recover anything?
So if we have enough code symbol, we are going to be able to. So one thing to note that is that when we are retrieving these code symbols, many of them are going to be erasures, because we only need a small amount, like say code symbols out of n symbols, which n is very large.
Sorry,
So this is going to be part of the analysis.
no, but can you go back to the last slide?
Yeah.
Because I think the main question is, can you sample CI and CJ under this constraint? Because if you can sample CI and CJ under this constraint, then you're fine. And also under the constraint that CI of 1 equals I.
And when we were choosing the parameters, we considered all these conditions to select the right N and K so that we both our setup succeeds and we are going to be able to search in a correct way.
So, but just, so since you introduced Reed-Solomon codes, it's clear you can do this for Reed-Solomon codes, right? If I want a particular output of the symbol to be a thing, I can find a uniformly distributed code word under these constraints, assuming the set of collisions isn't too big.
I mean, yes, if it's not, I mean, yeah, so then this is part of the analysis, right?
Right,
So you
so-
need to somehow trade off. Oh, yeah, okay, good.
So-
This is part of the analysis.
Can you go back to this graph?
Yeah.
Okay, so this is why she showed this graph. This is across all database records, what's the maximum number of collisions that could happen for each database record?
So if I inflate my Reed-Solomon parameter by an additional 14 or something, now I have enough degrees of freedom to
Yeah.
account for this extra pinning of things to avoid, to turn it into a map and still be able to run it.
Yeah.
Yes.
Okay.
So yeah, if we get enough code symbols, then we are going to able to recover the record that is close to the queried value. And in our parameter selection of N and K, we had 3 conditions. That the first one is that the probability that the close records, by close records, I mean the close records to the query don't match should be less than some negligible value. The probability that the far records match the query should also be less than negligible, and the probability that the setup fails should also be very small. And having these 3 conditions hold at once, we were able to compute some parameters that our construction would work on, and we were able to compare it to the baseline scheme that I talked about. So if we have a database of size M and alpha be LSH sizes and N be the number of required LSHs and K be the number of needed matches, for example, with the first setup, which is the error rate of 0.5 and 0.7, we,
Sorry,
yeah.
What are those error rates?
So when I was introducing the LSHs, we had epsilon F and epsilon T. Epsilon F was the probability that the far records match, and epsilon T were the probability of the close records have the same evaluation, LSH evaluation.
Okay, so just state, so this 0.5 means for
Epsilon F, and here it's epsilon T.
right, so 0.5 means for 2 biometrics, 2 different biometrics, the probability of the LSH matching is 0.5 for a single bit.
Yeah.
And for 2 readings of the same biometric, the probability of 2 LSHs matching is 0.7.
Yeah. And with this setting, we had an improvement from the baseline scheme. In the baseline scheme, we needed 10 to the power 10 number of LSHs, while in the same setting, we decreased it to 10 to the 7. And it was the same for many of our settings.
So just, there's a lot of information on there. Assuming I didn't write this paper with you, what should I be looking at? What's the most important thing to look at?
So for the one of the most important thing we were looking for is that how many matches we needed, how many LSHs we needed to sample.
So why is N an important parameter for the system?
Because for the accuracy, for reasonable accuracy, we wanted to see how many LSHs we need, and since N makes the construction to act to run faster.
So
We-
n determines the size of the map or the multi-map.
Yes.
So bringing n down
Yeah.
makes you use a smaller.
Yeah.
You should move on to the
Okay.
real data because this table's scary.
Yeah. Okay, so let's see the results of our implementation. So we implemented this construction and we tested it on both random and real data. For the real data, we used the IITD dataset, which contains the iris data of 224 people. For random data, we could test on higher size dataset like 10 to the 4 and 10 to the 6. The correctness result for the real data set was that for the setting that we had the LSH size be equal to 25, we needed 2000 LSHs and 30 matches to be able to decode. And the setup would succeed in just one iteration because we set this constraint that if setup fails, we would continue running it up to sometimes that setup succeeds and we could continue doing the search. In that case, we had 89% of true accept rate with 0 delta var. And delta var measures what fraction of database is incorrectly returned.
What's C here?
Sorry?
What is the difference between close and far?
So
There's a constant.
yeah, so the parameters we computed here for the so this computation is for the random data because random data are satisfy the well-spread conditions we defined before. And when we were computing them, we put C to be equal to 1. Yeah. But for the real data, since it's not well spread on the tails of the histogram of the distribution of the real data, we had to tune these parameters. So for example, if we had a database of 10 to the 4 and we have this setting, we kind of used a bit higher and lower values to see in what value the setup succeed, and we got this value. So since it is determined manually, we cannot determine what C would be for the real data set. And for the places that delta var is not 0, it means that the corrected value was not what we expected. But the good thing there was that it wasn't corrected to an integer. So we would know that that result is not correct because we were encoding the indexes which were in integers. Okay, so this was the work that we had done so far. We also were doing 2 other projects. The first one is designing a multi-key searchable encryption from private information retrieval and attribute-based encryption. There are private information retrieval schemes which use locally decodable codes, and we are looking to use them for our constructions. The other project that we have started working from more than a year ago is range queries over encrypted multidimensional data. The first phase of this project is finished, and now we are doing the aggregate range queries over encrypted multidimensional data. And we are using some data structures like segment trees, and we have some candidate cryptographic primitive like accumulators to be able to design such scheme. Our publication so far is as shown in the slide, and yeah, thank you.
So just question, so just to, that first paper, upgrading fuzzy extractors, not planning on having that in your thesis?
No.
The
The second one is this talk.
third one, we'll be hearing back from in a week.
Yeah.
And that is or is not?
This one does not have enough content relevant to my thesis, but the following paper to this, which contains the aggregate range queries, is going to be on my thesis.
All right, so technical questions from the general audience? Can you?
Yeah, can I have a question?
Yeah.
Can you go back to the table of the numbers, which is the performance results that you have?
This one?
Yes.
Okay.
So alpha is the size of each LSH, and then can you check? I'm just looking at the first row and the last row.
Yeah.
Right. So yeah, can you comment on the relation between alpha and the results that you have? Because to me, when you make alpha larger, I assume that you are providing more information, which will make the accuracy higher, right? So at least this is kind of how I understand it, and correct me if I am wrong. And you are even working on lower number of LSHs. So is that the reason behind the lower accuracy for the last row as compared to the first one?
Okay, so yeah, alpha is the size of the LSHs, and when I'm talking about the size, let's assume each LSH returns 1 bit. We made LSHs to be concatenated to make a bigger size LSHs. So alpha is here, if alpha is 25, meaning that we are concatenating 25 LSH outputs together, and in order to count it as a equal LSH evaluation, all these 25 places should be the same. So it's
Oh, so it's a higher restriction then,
yes.
because yeah, with 30 you need all 30 to match, but
Yeah,
with 25 it's lower. Okay,
Yes.
and the N is the database size that you are searching with them,
Oh no,
right?
N is the number of LSHs. So the size of the database is 224 because this is the higher database size that we have for the real data available.
But you also have data. You also have random. You've also tested on random.
Yeah. So if I want to show you the correctness on random data, it's as follows. So we tested on random data, and it's on the database of 10 to the 4.
Okay, and because kind of having this negligible probability to be 0 is impressive, right? So how do you envision that this will apply to the real world? So do you think that, I don't know, these numbers will match with real world databases? You'll be obtaining like this 0 more often, or it is just because of the experiment setup?
I think the correctness would be somehow the same, so we would get 0 or close to 0 delta var. Because the number of LSHs is still high, and for bigger size data set, it may take more time to, the search get completed.
Just got it, a follow on, I don't know if I'm audible, but for both.
Yeah, I hear you.
For both the baseline scheme and this scheme, you can eventually find an alpha and N that work. It's just whether they're viable. So basically when you, as long as there's a gap between the match rate of close and far things, you can pump alpha and N up enough so that you have a reasonable system. It's just, do you, like the table Maryam showed, do you have to set N to 10 to the 10? In which case, nobody's ever going to use this thing because,
It would be super inefficient.
it's way too
Okay.
big.
Okay, so okay, just taking that backward, it means that before using your system, I need to run some preliminary experiments on the database that I have to configure these parameters, or do you have, as part of your work, some guidelines on how to set up these parameters, or I don't know, deriving lower bounds and such, saying that, okay, if you stick to these lower bounds, you will get, I don't know, delta far, or these like negligible probability between this and that, and the target rate of receiving the correct match will be between this and that. Do you do something like that in your paper, or are you planning to do something to that extent?
Yeah, so for the random data, when we were computing, we have included it in the table in the paper. We are using the Chernoff bound and the number of places that Ritz-Solomon codes can correct. Then, according to that, and according to the distribution of the real-world dataset, if it's close enough to the random distribution, it needs some experimental tuning to, change alpha and until the setup succeeds. And so one thing to note that is that the case where we needed to change these parameters was that for the setup to succeed.
Okay.
So we would know if in a first run we would know if the parameters alpha and N that we have for random data would work on the real data set, and then according to that we can just use a bit lower or higher N and alpha to change that and see if the setup works.
Okay. And yeah, if I can have another question, I'm not sure if the time permits. Is it okay to ask another question?
Yeah, sure.
Can you speak a little bit about the accumulators and where are you planning to use them? Is it to optimize the size of the response that I'm getting, so you'll accumulate these things together, or is it on the database side that you will accumulate the database and so to perform the search, I don't know, faster or something
Yeah.
like that?
So for the aggregate queries, we have decided to use segment trees. Segment trees are a kind of trees that in the leaves, they include all the records, and in the middle nodes, they have the accumulated value and other information of the data set. One problem is that for the sparse data, we would get some efficiency problem if, for example, the tree is not balanced, and we want to know if the right-hand side range or the left-hand side includes in the query or not. So we are planning to use accumulators to see if, for example, one range or one member includes in the following ranges. I mean, by following, I mean the lower levels of the tree or not.
Okay, so yeah, so it is to optimize the search on the database side, but
Yeah,
that the responses will, okay, that makes sense. Yeah, thank you so much, and it was a great presentation. Wish you all the best.
Thank you.
Just for a time check, let's pick out sorry for expelling people. It always seems like such a me. And certainly for others, if you have to go, no. Okay. Walter, Alex, I guess starting with you.
So,
I could just ask an easy one. So this is your proposal, right? So what are your plans to finish? What's your expected timeline?
So we have planned to finish on the spring 25.
25. Okay, good. And what do you have left to do? I'm sorry, I might have missed it at the end of your talk, but
Yeah, no problem. So we have two
yeah.
in progress projects. One of them is multi-key searchable encryption, and the other one is the aggregate range queries over encrypted multidimensional data. For the second one, it's a long time we have started this project and we have the idea. The first one, we also have some candidate idea and we are working on it. So it's a newer one, yeah.
Well, but just
Yeah.
to strengthen that, I think the ideas, we have pretty high confidence that both of these ideas work.
Okay, good.
So it's not, I tried to have Maryam only put up things where we have confidence that the ideas work. There's substantial writing and writing proofs that still need to be done. But I think it's a pretty low probability that in 3 months we're like, oh, these ideas didn't work.
Okay, good. Cool. All right, thanks. This was a great talk.
Thank you.
Okay, so Walter asked the question I was going to ask, which is,
Yeah.
so what exactly is the proposal for, so what's the plan? So what you, as I understand it, let me try to answer my own question.
Yeah.
So as I understand it, you presented today basically a completed part, a more or less
Yeah.
completed work unit that will be part of your thesis. I agree with what everybody else said today. Great job presenting that, by the way, and it seems very interesting. And as I understand it here, you have two other projects. The first will not actually be reflected in the thesis, and the second, is that
both of these are going to be reflected in our thesis. So we have a submitted paper on the second one. That paper is not going to be included in my paper because it's going to be in other people's dissertation. But this project is not complete because, well, the first one didn't include the aggregated part. So we were exploring the range queries over encrypted multidimensional data. Now, as a follow-up work, we are exploring the aggregate range queries over the scientific data sets.
Okay, so at the risk of forcing you to repeat yourself,
Yeah.
Aside from the excellent completed work that you talked about today, what exactly are the plans for the rest of your thesis? And maybe can you give the technical work there a 30-second description of what it is?
Yeah, sure. So the first one is going to be multi-key searchable encryption from PIR and ABE. And
what is multi-key searchable encryption?
So multi-key searchable encryption is a kind of searchable encryption that multi-user can query a remote server, and well, they can share files in a remote server, and each of them can search that remote server and receive all the records of other users that have that keyword searched. So, and we want them to have each one of the user have their own special key.
Can you give an example of an application where several users who have separate documents, right? Because each one, they have them under their keys, but they want one response to come to all of them. So this will also reveal something about the others, right?
So
can you give an example of an application?
So we don't want any of the users gain any information other than the received documents, and the application.
Well, and just while Miriam's
Same
thinking,
thing.
I want to stress, like, this is new in this setting, is that every work in the multi-client setting has always assumed like leakage. And so like that's the new.
Yeah, it's natural, right?
Right. So this is the new thing, is that you only receive documents that have, or can only process things that have been shared with you, but don't learn anything about what's been shared with other users, and the server doesn't learn anything about what people are querying. So that's
Okay,
like
okay.
substantial, new, and different than prior work.
And
An adversary also does not learn this, even if they snoop on all the community.
Even if the adversary controls the server, some subset of clients, and the person who set up the database. That's the goal.
Okay, I see. So with a fully adversarial server, still what's protected? Yes, what's protected? Sorry. So the only information that I learned.
it is the document that contains this search keyword.
Well, no, so if I control the data owner, some clients, what's leaked or what's revealed to the adversary?
In a secure setting.
What, basically, what's the game? Right, what's the leakage? What's the security definition we were looking?
Yeah, so we wanted that the adversary, even if we have some users that collude, don't learn about the documents themselves, I think.
Documents that haven't been
The
shared.
and key, yeah.
Okay, but as a part of the group, which is my key is part of this multi-key group, I will get the same response as everyone else, right? So if it is me, yeah, if it is me and you, and we both have documents in this database, and we issued this key under both of our keys, then the response of that query will be delivered to me and you. But whatever, anything else in that database, in your database, I'm not going to know anything about it, other than what the response will reveal. So is that kind of like the setup?
Yes, other than so we don't query in a group, but yes.
But
We can, okay. So it is just based on this query requires processing of documents that are encrypted under several keys. So this is kind of like the thing.
Yeah.
I see. Okay. Yeah, because my follow-up question, if it is the former, I don't know, did you think about some threshold setup where there is a group and like threshold of them will show up and so on, but apparently it's not the same setup.
And just for the people that are here too, one thing that I didn't have Maryam put question is we use Solomon codes in the work she talked about today because they handle erasures, they handle they handle correction, and they have this condition that, hey, I can make code word symbols equal and I can sample the rest of the code. There's a question of whether you can design, sorry, and let me say one more thing. And your errors are only ever other code word symbols. They're not like truly random things. So this is not a normal error channel. I think it's a nice question of whether you can design better codes for what I just said, right? Where I'm going to like lay out a matrix of things that need to be independent, but that you can recover more errors knowing that your errors are going to come from this list. And we've thought about it, and I don't know. I haven't thought of anything. Maryam hasn't thought of anything, but I think it's
I put it in the prospectus if time allows, but
Great.
for the same reason I didn't put it here.
Yeah.
Yeah, so the main project is range queries over encrypted scientific databases, which scientific databases are usually multidimensional and have a very large size. For the first phase of this project, we have submitted a paper exploring how the data structures and the query shapes can affect the leakage of the search scheme. And as a follow-up work, now we are going to design an aggregate range queries over aggregate range searchable encryption scheme.
What's an aggregate?
So for the aggregate function, the statistic functions that we are considering right now are sum, mean, median, and mod. And yeah, so a user might query a range and would get back the aggregated value in a data set that lies in that range.
Aggregate.
So one of the things that we need to do right now is to extend the idea we have, which is the segment tree, to multi-dimensions. So a user might be interested to do the aggregated evaluation over multi-dimensions.
But assume the thing you're aggregating and the thing you're searching on may or may not be the same dimension.
Oh, I see. So I give a range.
Yeah. Yeah.
Right. So for this geographic region, what's the average temperature? Time series as part of Connecticut, what's the percentage? All right. Why don't we have you?
Yeah.
Also, I'll stop recording if I can remember how to do that.